The first law of thermodynamics is a very essential part of our understanding of how engines work and of the flow of energy. We're going to first begin with a bit of a demonstration. Consider two balloons. The first balloon is filled with air, and the second one is filled with water. Both are exposed to heat. This type of exposure is going to be convection because it's involving a fire and a gas in this case, as well as fluid. So balloon 1 has air, balloon 2 has fluid. This is convection. Which balloon will take more time to pop when exposed to heat?
Goodbye.
So we notice, of course, that the balloon that was filled with water took a substantially longer time to go ahead and pop. The reason for this is because the amount of heat that was required. Obviously, the balloon itself requires a certain amount of heat to go ahead and pop it. But when we also have it filled with water, it's going to be the heat of the balloon plus the heat of the water that's necessary to go ahead and get the balloon popping. It's a substantially more amount of water, amount of heat, especially because the water has a higher specific heat than the air does. So heat flow and work are two forms of energy transfer, right? We're talking about conservation of energy. We're talking about keeping track of where all the energy is flowing, okay? Of course, heat's going to flow from high to low, okay? And it tends to be spontaneous. We're not quite sure, we can't predict exactly how it flows, but we do know that it flows, and it goes from area of high to an area of low. All right, this is what the first law of thermodynamics is all about. So if we're going to change the thermal energy of an object, delta U, remember thermal energy is related to the temperature of an object. So if you're having a hard time getting your mind around thermal energy, you could kind of think of its cousin, temperature. Okay, if that helps. The thermal energy of an object is equal to the heat added to the object minus the work done by the object. And so we're going to express this as the first law of thermodynamics. However, sometimes they make it a plus, and that's because as work is done on the object. So in the first case, the one that we're going to refer to with a minus is work done by the object versus work done on the object. And we'll make the distinction as we give some more examples.
I just cannot believe this!
Problem 1. Let's draw a simple heat engine. So the way these look is you have what we call a hot reservoir. Okay? This is traditional talk.
Could you say that again,
a hot
please?
reservoir, the word reservoir, if you're not comfortable with that word or how it's being used, it's a bank. It's a station. Okay? It's something that's going to be given heat. So I have heat storage. If storage is a better word for you, think of hot storage. Okay? So I have this area, this reservoir, this storage that's full of hot, high temperature energy. I have this engine. Okay. And then I have, so this is going to be the engine. and then I have what's called a cold reservoir. Now, don't be fooled. It's not cold. It's not a refrigerator, okay? It's called a cold reservoir when it should really be called cooler storage, okay? It is not as hot as a hot reservoir, and what it does is pretty much waste energy. Waste energy goes in here. So in this hot reservoir, I have a temperature in Kelvin. Okay, it's high. And I have, in this hot reservoir that's at a high temperature, it releases energy. That QH is going to be the heat from the hot reservoir. So the Q is the heat and the H is the hot reservoir. And it's going to deliver heat to the engine. The engine will go ahead and pump out work. However, there is no 100% efficient engine. And so it's going to go ahead and take all of this heat, convert some of it to work, and then spit out the rest as waste energy. We call this the heat transfer, right? This is the heat going to the cold reservoir. The cold reservoir will be at a lower temperature. Sorry, I don't know why I did that. And I need you to focus on a few things here. One, there are temperatures in this reservoir. Those belong in the reservoir. Okay? 2, the arrow represents the energy transfer. So the QH is not the reservoir. The QH is the arrow. It's the heat that's being transferred to the engine from the hot reservoir. QC is the heat being transferred from the engine, the leftover energy that wasn't used, leftover heat that wasn't converted to work is being transferred to the cold reservoir. Okay. So an important note: make sure that you're hot and you're cold. This might be a left column idea for you. Make sure that you're hot and you're cold reservoirs. That the temperature needs to be in Kelvin. All right, it's really very important in the future. Make sure it's Kelvin. If we look at this flow of energy, we can make a few equations based on this. And understanding how this diagram works and where the energy is going is really important to your understanding. If you need to invest in something to focus on in this lecture note, problem 1 is it. Make sure you understand problem 1 deeply. Okay. Now, let's look at the relationships. So, I have all this heat coming from the hot reservoir. That's split up between two things, the work and the cold reservoir. In other words, if I start off with 800 joules and I pump out 500 joules of work, then I dump out 300 joules of waste energy. It's just balancing things out. It's just adding them up to make sure they all add up. Okay, that's just an example. Now, along the lines of that, we could also find out what work is, right? Work is going to be how much I started minus how much I dumped out. We could also express the energy as the waste energy, right? That's going to the cold reservoir, that waste heat. That would be the subtraction of QH minus QW. So the first law could be expressed in terms of a heat engine. You'll notice that this looks a lot like our first law, right? First law said delta U is Q minus W. You'll notice a very, very amazing similarity, for example, to this one right here, right? Why is a simple heat engine diagram helpful with explaining the first law of thermodynamics?
When you gotta go, you gotta go.